Hi there, welcome to Chapter 5, Lesson 1, Exponential and Logarithmic Functions. And this lesson should pretty much be a review of what you learned in pre-calculus, but we're going to be talking about both exponential and logarithmic functions this chapter, so it's worth taking the time in the beginning here to review, make sure we're all starting in the same place. The first thing we're going to do is looking at what an exponential function is. And what an exponential function is some a to an x power. Now it's important to note here that a is a constant and x is the variable. A is thought of as being positive, and we say a isn't equal to 1. Otherwise we just have 1 to the x, and that's just 1. That would be a constant function. So an example of an exponential function would be, for instance, y equals maybe 2 to the x power. Not x squared, though, for instance. Remember, this has to be a constant, and this has to be a variable. That's what makes it an exponential function. Okay, and we have the constant in this case is what we call the base, and then the x variable there is what we call the exponent. All right, and so this is probably one of the functions we're fairly familiar with. Similar to this is a logarithmic function. In fact, a logarithmic function is the inverse function to an exponential. In a logarithmic function, we can basically think of y equals log base a of x. And the way that we can sort of think of this is we're asking ourselves, a to what power would equal this x? And whatever that is, that should be y. And so basically whatever a logarithm is solving for, in this case it's going to be y is equal to this logarithm, we can think of that as representing the exponent. It's the power here. A to what power equals that x? All right, and so another way that we can write this in exponential form would look something like this. X equals a to the y. And we can sort of see that all we've done is we've switched the x and the y, and that's what makes them an inverse relationship here. Okay. Similarly, we assume a is positive, and we assume a can't equal 1. Okay, now we have these properties of exponents, which we've become quite familiar with, I think, this year, particularly as we've done the power rule for derivatives and antiderivatives, but I'll just review them real quick here. A to the 0 power equals 1, where a is some constant. Now this is true for all values, except I'm just going to write this here, a cannot be 0. 0 to the 0 power would be undefined. If we have a to the 1 power, that should just be a, right? If we're multiplying two powers, we know that we should add their exponents, right, as long as they have the same base. If we're dividing two powers with the same base, we know that we subtract the exponents. And if we have a power raised to a power here, we multiply those exponents together. All right, and I'll just put a few other ones here. We can sort of distribute powers through in the case of multiplication or division here. So those are just some other properties of exponents. All right, so those are ones that I think we've used already quite a bit this year. Now, what we haven't done is we haven't looked at logarithms, and there's properties of logarithms that kind of directly follow from these properties of exponents. For instance, when we evaluate something like log base a of 1, what we're really asking ourselves is what is a to what power would equal that 1, right? So let's say that we don't know that answer yet. We'd be asking ourselves a to what power equals 1. The answer here should be 0. Right? It doesn't really matter what a is, as long as it's positive. We're assuming that a isn't equal to 0 here. And then we can say that the answer here should be 0. And that follows directly from this property of exponents. Next, if we ask ourselves a to what power is equal to a, right? That's how we evaluate this logarithm. It should be 1. Right? It doesn't matter what a is, as long as we put a 1 in that exponent, it should still equal itself. All right, so those are some two common properties of logarithms, ones that we want to be very familiar with. Next up, we're going to look at, I'm going to sort of group these three together here. If we're multiplying something on the inside of a logarithm here, that becomes the sum of two logarithms of those individually. So we can say the log here of m plus the log of n. All right, so multiplication on the inside means addition on the outside, is how I like to think about it. If we're dividing on the inside of a logarithm, that means we're really subtracting two logarithms. And these do follow, by the way, if we're doing like a multiplication here of powers, we add exponents. It's the same idea here when we're doing a product here, we're multiplying here, we're adding the logarithms, and logarithms, remember, represent the exponents. And it's true if we have a quotient here for dividing, it's the subtracting of the exponents. So these actually do follow directly from there. This last one here I'm going to mention, number 5, is my favorite property of logarithms. And that is if we have a power inside of a logarithm, we can take that exponent, that n, and bring it out front as a coefficient. It's a really useful property. We'll see that getting used here a little bit later in the lesson. I'll just mention these briefly. If you've learned logarithms, you've probably learned the change of base formula. This is what we use in case we have something like a log with a base of something other than something maybe we're used to. Like if I look actually to the very last example, number 6, this log base 3 of 10, we can say that this is going to be the log of some value, we're going to say b, some base, so we can choose whatever base we want, but that 10 is going to be here, over a log, and we can choose the same base here as the top, whatever we chose there, and this is going to be of a, in this case it's going to be 3. And so I can choose anything I want here. This could be a 4, for instance, if I wanted. It could be a 7 here, if I wanted. Right? By a ratio here, these should be the same. And I can actually just choose log. This is what we call the common log. Let me get to that here. The common logarithm is so common, in fact, that we don't usually write that base there. We sort of save ourselves the time. If you ever see this log without a base written, we're going to assume that that equals a 10 right there. And so actually, what I've written here is correct notation, and log of 10 should equal what? Remember, we're asking ourselves 10 to what power is equal to 10? It should be a 1 here. And so if we wanted to evaluate this one, we could just say this is 1 over log of 3. In fact, since I have the answer here to this very last one, I'm just going to skip down to this and say this should be 1 over log of 3 for that same reason. And the nice thing about that is this is a button on our calculator, or at least most calculators have it, the common log. We type log of 3 and then figure out what is that value. We can actually get the decimals there. Okay. Now, I don't find this change of base formula too useful. I'll show you later on in the examples how we can actually avoid ever having to use this. Let's get back to the common log, because this is a button on our calculator. So is the natural logarithm. The natural logarithm you've seen before is when we write ln. And if you ever see that, all that means is a log with a base of e. And e, if you forgot what that is, that's what we call Euler's number. And it's this number here, 2.7 something, 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 something. In fact, for this class, you'll just need to know it's about equal to 2.7. Now, if you want to know more, you might notice that 1828, 1828 happens to repeat itself. Just a coincidence, but if you can remember that 1828, then you can actually remember the next 8 digits. And the last 6 here that I listed here can actually be memorized fairly easily. If you remember in geometry, we talked about a 45, 90, 45 triangle. Right, so that's actually an easy way to remember this. Anytime the word natural gets used in math, we're referring to this number e. In fact, this is sometimes called the natural number. More commonly, it's called Euler's number because Leonhard Euler was the mathematician who clearly identified what this number was, and he gave it its name. In fact, he was asked once, did you name it E because your name starts with an E? And he said, no, it stands for exponential. It's sort of the natural exponential base. But I don't know, I kind of want to believe that he just used that as a coincidence here, that he must have chosen E because it was his last name. It also began with an E. All right, and the last thing I'm going to look at are these. There's really only 2 inverse properties here, and that's if we have a log with a base of a to the something power. In this case, I called it u. These sort of cancel out, and this should just equal u. And then a similar one here is if we have a raised to the log base a power, those cancel out there, and we just get u for that as well. Now, if I choose a specific a value here, like 10, then what we really have is log of 10 to the u should be just u. Right? Log of 10 becomes 1, and it cancels out here. Same thing here, if we have 10 to the log power, that cancels out, we just get u. And if I choose instead of base here, instead of a, I'm going to say e, well, we can say ln e then, those cancel out to get u, and e to the ln cancels out, and we get u. So those are nice things to get together if we have log of 10 or ln of u. All right, now that's enough review here of the properties. Let's jump into some actual examples. Number 1, I say expanding logarithms. Now, You might be wondering, how can I expand this logarithm? Expand means kind of write out as multiple expressions here, as multiple logarithms. Well, in this case, I'm not really sure I can expand it, although I can think of this as a base of 10. We can ask ourselves, 10 to what power equals 1,000? And it should be a 3 here, and in fact 3 is going to be my answer here. I just want to show you though that this can be seen more clearly if we write this as log of 10 cubed, right? And we can also see that that 3 comes out, the log of 10 cancels, and this should just be equal to 3. Let's look at part B, the natural log of 3e squared. Now when I say expand here, basically I'm looking at these 3 properties, numbers 3, 4, and 5 here. We're looking inside the logarithm for times, divide, or exponents, because if we have any 3 of those things, we can expand them. Notice if we are adding or subtracting though inside the logarithm, we can't do anything with that, just times, divide, or exponents. Now if I look inside here, I sort of see 2 things happening. I do see multiplication. We're saying 3 times e squared, but that square is also an exponent, which means we're going to be able to use that property in a moment. Because right now it's not the whole thing squared, it's just the e that's squared. So I'm going to start by expanding this as ln 3 plus ln of e squared. Right? So whenever we see times in the inside of the logarithm, we can think of this as a plus on the outside. And the last thing I can do is I can look at this ln e squared. Remember that 2 can be brought out front, and ln e is just going to be a 1, that cancels. And finally I can say this is an ln 3 plus 2. Right, so I can sort of use that inverse property here of logarithms I mentioned. All right, so that looks expanded and simplified. Next, part C. Well, that square root symbol, I want to rewrite that as a 1/2 power. We're going to have ln x to the 5 power, but it's 5 and then it's a 1/2, so we can say 5 over 2 power maybe. Write that as an exponent. That's a good idea here whenever working with logarithms, is to rewrite those square roots or radicals here as an exponent. Next, I can take that and I can take it outside. I can expand it outside using my favorite property of logarithms here. I can say that's a 5 over 2 ln 2. That looks fully expanded then. And I could figure that out on my calculator because the natural log, the ln, is a built-in feature, a built-in button on my calculator. All right, this next one we have ln of 1 over e. Now, I'm so close here. If this was ln e, it would just be 1. And I want to be able to cancel something out here because I have an ln, I have an e. Now, one thing we could do is we could rewrite this as ln e to a negative 1 power. Then we could use that inverse property here and say this should equal negative 1. And that is my final answer. The other way I could think about this is I could expand this as ln of 1 minus ln of e, right? We're dividing on the inside there, so I can say this is an ln minus an ln. What is ln of 1? Remember, we're asking ourselves e to what power equals 1? That should be a 0. Minus ln e, well, e to what power is e? Should be a 1. And this is a negative 1. We can get to the same answer this way. All right, so that's sort of how we can work to expand these logarithms and how we can simplify them. Let's practice the other way, and let's try condensing these logarithms. So I'm going to take multiple logarithms and put them back together. My goal is to put this back together into one logarithm. The first thing I'm going to do is I'm going to condense these coefficients using my favorite property. I'm going to put them back in as exponents here. So let me write this out here. This is ln x then cubed, plus this is ln of y squared minus ln of z to the 4th power. And the last thing I'm going to do is I'm going to just start condensing these. We have a log plus a log, so I can say that that's going to become 1 log, and we're going to multiply the x cubed times the y squared. And then I can keep on going here, and we're going to say minus this ln of z to the 4th. Well, minus a log means we're going to be dividing here on the inside. Let me just put parentheses around this. So we have a natural log of that whole expression there, and that's my condensed answer. Notice I have only one logarithm in my final answer. It's not log of x cubed times log of y squared divided by log of z to the 4th. That would be a common mistake. Part B. Again, I'm going to condense this. I'm going to start by looking for any coefficients like I did here before I try to condense those. I'm actually going to start inside the square brackets here. I don't see any coefficients in front of these. But what I do see are these minus signs, which means I can condense these logarithms using division on the inside. So let's go ahead and start doing this. We have ln of, this is going to be x divided by x plus 1. And we still have this minus ln of x minus 1, so we can divide this again as x minus 1. So I'm running out of room there. And I do want to simplify that. For instance, that's going to be ln of x over, and this is going to be an x plus 1 times x minus 1. We can put this all into the same denominator. We still have that 2 in front, don't we? Well, that 2 in front, I can actually condense that and put it up here as a square. And that could be my final answer. That's everything condensed into one logarithm. Okay. If you wanted to multiply that square inside the expression, you could. I'm just going to leave it. Number 3. How do we solve exponential equations? 2 to the 5x power equals 75. Well, the key is to solve for x is we need to get the x out of the exponent. And so one way to do this is we can find a log of both sides. The log of 2 to the 5x power should equal log of 75. Now, you may have even seen that you can choose a base of 2 here. And that's a nice thing to do because then that cancels out and we just get 5x equals log base 2 of 75. We can divide by 5 and get our answer. Now, some calculators don't know how to evaluate this log base 2 of 75, so I actually like to avoid this. I like to choose a logarithm that is already built into my calculator. For instance, this common log, the log base 10, should be a button on my calculator. So would ln, right, the natural log, but I'll just go ahead and use this log for now. You can actually use any log that you want because the key here is that we need to be able to use my favorite property here and pull that variable outside of the exponent. We can then write this as 5x times log of 2. Now, log of 2 is something my calculator can tell me. That's just some number, just like log of 75 is some number. If I want to solve for x, then I just need to divide everything. I need to divide the 5 and I need to divide the log of 2 over to the other side. So finally I can say x should equal log 75 divided by 5 log of 2. Now when you type this into your calculator, make sure you type it in like this, log 75 divided by 5 log 2. Now this is a mistake if you type it in this way because your calculator is actually going to do the division first and then it's going to multiply. But instead what we want to do is we want to divide this whole denominator. So make sure you use those parentheses right there when typing this into your calculator. Okay, number 4. We're going to try solving this logarithmic equation. Now, how do we do this? Well, it'd be a lot simpler if we could somehow get this into just one logarithmic expression. And we can do that. We can condense this. This should be a log base 3 of x times x minus 2. Now, once we have this into one logarithmic expression, how do we get rid of the log base 3? Well, we don't divide by it. That's a common mistake because we're not really multiplying by a log base 3. Right? There's not multiplication happening here. And so we need to do the inverse of what a logarithm is, and that's an exponential. In other words, we need to say, what is 3 to the log base 3 power? That's of the left side. And then we say 3 to the 1 power, right? That's on the other side. So we take both sides of this equation and we raise them into the exponent. And we choose a base of 3, although we could have chosen any base that we wanted. I chose a base of 3, though, so that I can cancel out using that inverse property here. And so finally what we get here is an x times x minus 2 equals 3. And that's the equation we're really trying to solve. All right, well, if I want to solve that, I should multiply this together. I get x squared minus 2x. I'm going to move the 3 to the left side so this equals 0. And then I can factor this x minus 3 and x plus 1 equals 0. So finally we get x equals 3 and negative 1. Now actually, this is a mistake. That isn't my final answer. When solving logarithmic equations, we've got to remember to check our answers. Like if I put a 3 in here, I get log base 3 of 3 is 1. If I put a 3 in here, log base 3 of 1, that's going to be 0. And I do get a true answer. So if I plug that in, it does check out. But if I put a negative 1 in here, we get a problem. What is log base 3 of negative 1? Remember, we'd be asking ourselves 3 to what power equals negative 1? And this is actually impossible. There's no answer that will make this true. Even if I put a negative 1 in here, 3 to the negative 1 power is just 1 over 3, a positive number. So actually, we can't have negative numbers inside a logarithm. We can't have 0 either. This would be undefined. And so actually I have to cross this one out. This is what we call an extraneous solution, an extra answer, a false answer. So x equals 3 is actually my only answer. It's a nice reminder here when solving logarithmic equations is we have to double check to make sure we don't have any of these false answers. Okay? All right, and so let's look at these last three, or I guess we already did number 6 here. Let's look at these last two then, number 5, A and B. I say solve using properties of logarithms. You might notice x is already solved for, so I don't really need to solve for x. What I really need to do is I need to simplify or evaluate this logarithm. We can say x is equal to, well, notice I have a division happening on the inside of a logarithm, so I can expand this as a log of the top minus a log of the bottom. I'm going to rewrite that square root here. It's always good to do that. I always do that in my first step as a 1/2 power. Now we can use the inverse properties here because we have log of 10 canceling out, so we're just left with a 2 right there. Minus, now this 1/2 can be brought out front using my favorite property here. We can call that a 1/2 log of, now what we have left here is 2 times 10 cubed, right? We can do something with that multiplication on the inside. Once we have a multiplication on the inside, we can think of this as really the sum of two logarithms. This is log of 2 plus log of 10 cubed. Now that 1/2 was being multiplied by everything here, so I do want to make sure that I have some square brackets around that. Okay, and lastly, I try to simplify this. Notice we can use our inverse property here. Log of 10 should cancel out. That leaves us with just a 3 left. Let me write this out here. So we have 2 minus 1/2 log 2. And if I distribute this negative 1/2 through here as well, we're gonna get times the 3 is a negative 3 over 2. So my final answer here I can say is 1/2 minus 1/2 log of 2. All right, and this last one, 5b. Now, I'm going to start with what's inside the parentheses. Now, I'm going to actually start by condensing this one. I'm going to start by putting this 4 back in using my favorite property here. And so we can say this is a 1/2 natural log 2 plus ln 2 to the 4th power. What is 2 to the 4th power? Well, that should be 16. And I can actually condense this together. We have ln 2 plus ln 16, so a plus on the outside means times on the inside. This is a 1/2 ln of 32 then. And then we can use my favorite property again. We can put the 1/2 back in, and that's really like a 1/2 power is really like a square root. And so finally we can say x is equal to ln square root of 32. And if you really wanted to, we could even simplify this. We'd say this is ln of square root of 32 can be thought of as a 4 square root of 2. And that's going to be my final answer.